Today is gonna be part 2 of SVD. I think on Monday will be part 3 and the final part, some applications to it. And Wednesday we're gonna do this invited guest lecture on multidimensional scaling. So that's not mandatory, but it's recommended. And I posted the final project number 6. If you have noticed that on Canvas, the mini Google. That's about PageRank and an application of SVD called latent semantic indexing. So take a look at it. Oh, an important thing about a project number thing. I mean, it's there on Canvas, but it's going to be due in 2 weeks, not in 1 week, because in 1 week would be exactly Thanksgiving, so it wouldn't be good. All right, so we are doing single value decomposition, aka SVD. Oh, sorry, I need to zoom in, make it bigger. And I did start recording it, right? Wait, yeah, focus. That is running. All right. So if I should formulate SVD as a theorem, then it says that if I take an arbitrary real matrix, then I can always find, I'll just write it short, or maybe I can write it like exists a matrix U from R m by m, matrix V from n by n, so they are square, and they are both orthonormal. And matrix, I guess I should put exist everywhere, and the matrix sigma, which is a little bit funny, it's an m by n matrix, and it has this form. There is sigma 1. It's sort of like diagonal, but for the diagonal analog in a rectangular matrix. So it's m by n, so it's rectangular, but the non-zeros are confined to this little square, and they are just on the diagonal. So here everywhere else are zeros. And moreover, we can always find the SVD such that the sigma 1 is the largest and the sigma r is the smallest, and even the sigma r is strictly greater than 0. So otherwise it would be, I could truncate it earlier, right? So this is just to say that sigma r is the last one that's non-zero. Where this R, guess what is this R? You know that, right? The rank, exactly. So it can happen that it goes all the way, right? If the matrix happens to have full, in this case, row rank, or if this picture is for the case where n is more than m, in the other case the sigma would look like this, and the individual elements would go like this, right? Eventually you run out of the diagonal. So that's what happens there. So the theorem says, single value decomposition says that for any matrix A, I can find matrices U, V, and sigma such that A can be written as U, D, V transpose. So this is the single value decomposition. We decompose the matrix A into 2 orthonormal matrices, U and V, and this, oh sorry, D. Sometimes this is called D, but here I called it sigma. The D like diagonal. So we decompose the matrix A into 2 orthonormal matrices and 1 matrix that's almost diagonal. I think it's called like rank normal form, the form of this matrix. Okay, so I tried to sort of describe how it works the last time, but I think we still need to do it in the general case. So the question now is, how do we find the U, D, and V and prove that it's always possible? I mean, for any matrix you can always find this decomposition. So it's not like a general eigen decomposition where we have like all these funny cases. I kept telling you, oh, sometimes it doesn't work, sometimes there just isn't enough eigenvectors. The SVD it's not a problem. It's guaranteed to always exist. Okay, and the trick to find it, I think I sort of glossed over the last time, or I gave you a rough idea how it's done the last time. The main trick essentially is to look at ATA. So let's take a look at it. So we need to look into the properties of ATA, because that's the key to finding the the singular vectors and singular values. So we start with the matrix A, just like we started in the theorem before, which is a general m by n matrix. And now we do ATA. So if A was m by n, then ATA is n by n, so it's of course square, right? It's clearly symmetric, right? I've done it many times. If you transpose ATA, you get again ATA. And it's also very easy to see that it's positive semi-definite. Maybe it was like somewhere in your homework as well, I think. So it's easy to see. If you hit it with the left and the right with the same vector, if you do this double dot product, then this is equivalent to AX transposed AX, just because I can transpose this entire thing. This is of course just the norm of AX, and that must be a non-negative number, right? Square norm is a non-negative number, yes, for any vector, which means that the matrix ATA is positive semi-definite. And from what we discussed when we were studying eigenvalues, we know that if matrix is positive semi-definite, that's equivalent to saying that all the eigenvalues of it are greater than or equal than 0, are non-negative. And also because it's a real symmetric matrix, we know that that's the nice case where all the eigenvectors exist, that we have the full set of eigenvectors, and that they are real. Remember, this is the nice case when we have real symmetric matrix. Here it's even nicer because it's positive semi-definite, so on top of that the eigenvalues are non-negative. So that also means that we can find an orthonormal basis for the space R2n. This is an n by n matrix, so that means that we can find a basis which is formed by eigenvectors of ATA. So if I find the eigenvectors of ATA, I will find n of them, and they're going to be real. And I can call them VI, so they go from V1 to Vn. And because, here is a little trick, because the eigenvalues were non-negative, I can take the square root. So instead, so this sigma I squared, the sigma I is essentially the square root of the eigenvalues, which I can do and be real because they were non-negative to begin with. So of course when I square it, sigma I squared is just the eigenvalue, and this is true. So this just summarized what I just said, and because we have a full set of these eigenvectors, we can put them in a matrix, and the V is now going to be an orthonormal n by n matrix. That means that VTV is In, and that's also equal to VBT. And these V's, as we will see in a little bit, they will be the right singular vectors of A. But before we do that, let's take a look at the null space of A. We eventually have to tie it all together with the 4 fundamental subspaces, the null space being one of the 4 fundamental subspaces. So let's look a little bit into that. So the null space of A is defined as all vectors that give me 0 when I multiply from the right with, when I multiply them by A. And the interesting thing is that the null spaces of A and ATA are exactly the same. We might have discussed it before, but it's definitely good to think about this again in this context. So I claim that the null space of A is exactly equivalent to the null space of ATA. This essentially points out to the relatively close relationship between the two matrices, right? They are not the same, right? They don't even have the same size. This is a rectangular matrix, this is a square symmetric matrix, but they happen to share the same null space. Why is it true? So first, if I have anything in the null space of A, then it's also in the null space of ATA, right? That's relatively simple, because if it's in the null space of A, that means if X is in the null, okay, maybe I could do like this. If X is in null space of A, then it means that AX is 0. Then I can multiply from the left with AT, right? That the 0 stays 0. That means that ATAX is 0, which means that X is in the null space of ATA, right? So that's proof of one direction, and I also need to prove the other direction. So if X is in the null space of ATA, then it means that ATAX is 0, just by definition of null space, right? And now I can, here comes the little trick. Like, the mathematics is combination of trivial things and little tricks. Then I dot it with X. So I put xt here. Of course, 0 stays 0, right? And this, if I do the transposition trick, I see that this is nothing but the square norm of AX. And if the square norm of some vector is 0, that's only possible if the vector itself, in this case the AX vector, is 0. So this shows that X is in the null space of A, which, if you put it together, then this shows that the null space of A is exactly equal to the null space of ATA, which is interesting, I think. I think we have done something like that, maybe probably in one of the previous lectures. Or, yeah. This one?
Yeah.
Or this one? Or the whole thing?
Yeah.
Okay, so let's go again. So this was the first part. That's the easy one, right? That's the one that says that NA is a subset of NATA. Oh my god. So this one you are asking about. So let's start. Let's take X from null space of ATA. That means that ATA times X is 0, right? So if that is true, that certainly it's also true if I multiply with xt, right? Because xt0 will be 0, right? Then xtat is nothing but ax, the whole thing transposed, right? And ax transpose ax is nothing but the square norm of ax, right? So what I have here is some vector z, which is different symbol for ax, whose square norm is 0, right? But the only vector whose square norm is 0 is a 0 vector, right? The moment there was something non-zero, it would show up in the norm, right? Even if it was negative, doesn't matter. So the conclusion is that the z must be 0, but I just use the substitution that z is ax, so ax is 0, which means that x is in the null space of A. Yeah, this is like very, very nice, clean proof. Just like putting lots of simple things, just stacking lots of simple things gives you something interesting. Okay. Okay, so now the interesting thing. Now we were talking about ATA, and this tells us that from looking at ATA we can claim something about A. That's essentially the high-level idea of this process. Because we couldn't find eigenvectors for A. A was rectangular to begin with, right? So we are working on ATA, and I claim that by looking at ATA, we can reason about A. So here is one thing we can already say about A. Because the null spaces are the same, then to find an orthonormal basis for the null space of A, all we need to do is to look for orthonormal basis of ATA, right? And the orthonormal basis of ATA is fairly simple, right? Think about that. If we did the eigendecomposition on ATA, what will be the vectors forming an orthonormal basis for the null space of ATA? It's written here, so you can also just read it and tell me the answer, but it's probably better to think about it. I'm looking for the space of all vectors x such that ATAX is 0, right? They have to be from Rn. I didn't write it there because I was lazy. That's the null space of ATA, which happens to be equal, as we just shown, to the null space of A, right? So if I want an orthonormal basis for this linear subspace, how can I get it? If I already have eigen decomposition of ATA, what am I looking for? Well, it's written exactly here, right? So I'm looking for the eigenvectors that correspond to 0 eigenvalues. Because if the eigenvalue is 0, that means that the eigenvectors will go to 0, right? Which means that they are exactly in the null space. And why I'm looking for eigenvectors is so that I get an orthonormal basis. We know, as I said before, that the eigenvectors of a real symmetric matrix generate orthonormal basis, not just the basis, but orthonormal basis. Okay, any questions? Yeah, like we can make it like more like a seminar if it's just so few of you, so don't be shy to say something. Okay, now what we need to do is figure out the relationship between the left and right singular vectors. So from ATA, what ATA gives us, or the eigen decomposition of ATA, gives us the right singular vectors. If we look at the matrix from the other side, if we do AAT, it turns out that we get the left singular vectors. And here we expose the relationship between the left and right singular vectors. So notice first that AAT is also a square symmetric matrix, but of a different dimension, right? ATA was, what dimension? Was n by n, right? So AAT is m by m. So they are of course different, right? They already have different dimension. But they are similar in the sense it's also symmetric and positive semi-definite. The same argument would apply, right? It's essentially just take AT here and you are back to the previous case. So I can do eigen decomposition of AAT, and I will of course also find orthonormal eigenvectors, real, and eigenvalues which are non-negative and real, of course. And here is the cool thing, the important thing. That's the relationship between the eigenvalues and eigenvectors of ATA and AAT. The left and right singular vectors. So here is the key derivation there. So if I have an eigenvector of ATA corresponding to eigenvalue sigma I squared, then this is true, right? Now I can multiply this from the left with A, and of course it still has to be true. So I put one A here and another A here. So it's ATA VI, sigma I squared AVI. And now I just use associativity, so I look at it this way. I just put the brackets right here. And what I see is that the vector AVI, what is the dimension of that vector? That's an m-dimensional vector, right? This is just an m by 1 vector. This is the same thing, right? And it turns out that AVI is an eigenvector of AAT, which is very interesting. More interestingly, with exactly the same eigenvalue as this guy here. So let me explain it once again in different words. So if VI is an eigenvector of ATA with eigenvalue sigma I squared, then AVI is an eigenvector of AAT with the same eigenvalue. Yeah, the same thing is written down here. So that's interesting, right? So now what we need to do is there's just like a little, my hand is shaking to say that those are the left singular vectors, and these are the left singular vectors up to a scale. So because I want the matrices to be orthonormal, the VI's the eigenvectors of ATA, they were orthonormal. I can find them so that they are orthonormal. But the AVIs are not necessarily unit length. They are usually not unit length. So I need to normalize them. But that's relatively simple now. So if I say that UI are the unit, that unit is the keyword here, length 1, eigenvectors of AAT, then I can put them into a matrix. Now it's going to be an m by m matrix, and it's going to be an orthonormal matrix. So UTU is IM, which is the same as UUT. It's a square orthonormal matrix. And now to recover the original AVI, the original AVI is the same as UI up to some scale, right? Because AVI were eigenvectors of AAT. UIs are also eigenvectors of AAT. You know that for eigenvectors, the length is unspecified, right? The length can be arbitrary, except for 0, right? Any eigenvector is equally good, no matter what I scale it with. So the scale here I can deduce from looking at the length of AVI, so square length of AVI, which is just VIT, AT, AVI, right? I just used the same formula as before. It should be clear, I hope. And what do we have here? Because ATAVI is sigma I squared VI, because the VIs were eigenvectors of ATA and the sigma I's were the eigenvalues of ATA. So the sigma is just a scalar, right? So I can pull it out. And because the VIs were unit eigenvectors of ATA, then this is 1. So this is just sigma I squared. So I can cross out the squares. So the length of AVI is sigma I. So the U's are, all I need to do is to scale the U's with sigma I, and I get AVIs. That's essential. Or you can look at it this way. The sigma is the length of the AVI vector, so I need to divide it by sigma, so I get a unit length eigenvector. And I want unit length eigenvectors, so I can just put them in a matrix, and I get an orthonormal matrix, not just orthogonal matrix. Because remember, in the SVD theorem, I said that the U and V matrices are orthonormal. So that's exactly what I am trying to do here. Okay, so now we have this relationship. So this is the relationship between the right singular vectors and left singular vectors through singular values. You can look at it sort of analog of definition of eigenvalues and eigenvectors, right? Except that now I need two different vectors there. Is that clear? All right. So now we have these funny vectors. Then we can essentially derive the singular value decomposition. One way we can look at it is the following. So because VI's are the orthonormal basis for Rn, that's where the matrix maps to, we can look at the action of the matrix in terms of the coordinates with respect to this basis. Or in other words, I can take an arbitrary vector x from Rn, and I can write it as a linear combination of the basis vectors, right? That's the definition of the basis. So in matrix form, if I stack these vectors v1, v2, and vn to a matrix V, as I defined before, the V is an orthonormal matrix. Now this can be written as y. And because it's an orthonormal matrix, I can invert it easily, then y becomes V transpose x. And now, interesting thing, let's take a look at the action of A on X. With action, I mean multiply A by X. So let's take a look at it. So if I multiply this by A, that means I'm multiplying this thing by A, right? This is the expansion of X, or the coordinates of X with respect to the V basis. And I know that AVI gives me sigma I UI, right? That's what I ended with the the previous slide, that AVI is sigma IUI. So I use this here, and I get that this is the action of A on X, which in matrix form, if I put all these vectors U in a matrix U prime, I can write it like this, right? Let's think about it for a second. So what this means is scale every column of U by the corresponding sigma. This means scale the first column of U by sigma 1. This means scale the second column of U by sigma 2, and so on. So that's exactly like this, right? Sigma 1 U1, oops, sigma 2 U2. And this just says take a linear combination of these scaled columns with the vector y, right? This is a vector like this, the y. And because y was nothing but VTX, I can write it this way, right? I plug in, instead of y, I just say it's VTX, and I see that the action of the matrix A on vector x can be written as this U prime, sigma prime, and VTX. Now why I'm putting these primes here is that because this is still missing the null space, but now that's relatively, those are the zeros there, it's relatively easy now to put it back. So in general, and this is the full SVD thing, this is the full SVD decomposition, single value decomposition, the matrix A can be rewritten like this, where U are the orthonormal matrix, so where U is the orthonormal matrix constructed from eigenvectors of AAT, V is the orthonormal matrix constructed from eigenvectors of ATA, and the sigma, this thing in the middle, that's the only rectangular matrix in the picture, is the m by n. It's in the rank normal form, so here is like a square. Maybe it's better to do like again this picture. Here is the only square that's non-zero, everywhere else is zeros, and this is a diagonal matrix. Moreover, because I can do any permutation of the columns of U and V, I can essentially permute these guys in any way I want. So the usual convention is that I permute it in such a way that sigma 1 is greater or equal to sigma 2, and so on up to sigma r, where sigma r is strictly non-zero. So this is how you can derive a singular value decomposition. And now how it ties to the four fundamental subspaces. The four that's really cool thing. The four fundamental subspaces you can immediately read from U and V. More than that, you can immediately read the orthonormal bases for the subspaces from U and V. So let's take a look at it. If the matrix has rank R, then we are going to have R non-zero single values in the sigma matrix, in the matrix of single values. That's what I said before, that there is the convention how to arrange that. You could be permuting things arbitrarily, but this is the standard convention. And now the first R columns of U will be an orthonormal basis for the column space of A. The first columns of V, or equivalently the first R rows of V transpose, they are an orthonormal basis for the row space of A, equivalently column space of AT. And the remaining n minus R columns of V, they are an orthonormal basis for the null space, and the remaining n minus R columns of U are an orthonormal basis for the left null space. So I would like to draw a diagram, which I think is much nicer than just saying it like this. So let me write like a graphical example of this. So if I have a matrix A, which is like this, this is A. It's an m by n matrix, and it splits into U. It's actually a good exercise to try to draw it by yourself, because then you have to think about the dimensions. M by M. This is U. Put it here. This is sigma. That's the rectangle one. and here is my V. And if I say that R is the rank of A, then I can split this U in the first. So this is size R, and this is of course size M minus R. Here is the non-zero portion here. Here's the sigma 1 to sigma R. Rest is completely empty. And here I can also split it like this. Here is like a demarcation line. Here is the first R rows of VT. So this is VT, the thing I'm looking at here. The transpose here is slightly confusing, so don't get confused. If I was looking at V, it would be the first columns. And the rest is N minus R, of course. Might be a good exercise to do the same picture for a matrix which is like this. It comes out basically the same thing, just to like make a little exercise. And now what I claim is that the first R columns of U are an orthonormal basis for the column space of A. The remaining columns of U are an orthonormal basis for the left null space. The first R rows of VT are orthonormal basis vectors for the row space, and the rest is the orthonormal basis of the null space. So compare this. I will explain this in a second, but I just want to compare it with this 4 fundamental subspaces picture. That's exactly what we see in the SVD. So the CAT, the row space, we read here. The null space is here, and we have orthonormal bases for these spaces. For the column space, we have the orthonormal basis here, and for the left null space, it's right here. And in these bases, what the matrix is just mapping some guys to zeros, that the null spaces are being mapped to zeros. And what the matrix is doing in the column and row spaces is just this scaling of each component. It's like non-uniform scaling, but with just exactly non-uniform scaling, just scaling of each coordinate. It's a diagonal matrix. So this, I think, is very cool. Now let me explain why this is true, why these are really the null spaces. It's sort of simple. So let's consider I take an arbitrary a vector which is an arbitrary linear combination from these column vectors. So let's take an x which is from the span of VR plus 1 to Vn. Which I should put the dimensions here, right? This is m by n, and this is n by n matrix. So let's assume I take a vector which is a linear combination of these rows or columns of V, rows of Vt, aka columns of V. So if I do Vtx, what I'm going to get, because this is an orthonormal matrix, then all these vectors are orthogonal to all these vectors, right? So I'm going to get a vector which is all zeros here up to R. So there is R zeros, and the rest might be non-zeros, right? So this is what I get with Vtx. Then if I multiply it with sigma, what do I get? Sigma is this, right? It only has non-zeros in the first R columns, right? If this has zeros in the first R components, what do I get? 0, yeah. It's just absolute 0. It's just everything is 0. So of course, if I hit it again with u, then that's u times 0, of course, has to still be 0, right? So if the x was a linear combination of these guys, then ax is 0. That means that x is in the null space. So I wasn't lying to you that this is an orthonormal basis for the null space. Those are really orthonormal vectors, and that they all multiplied with a give me 0. So they are indeed in the null space of A. See that? Very similar argument works from the left side. So if I take a vector x, maybe I should call it y, but yeah, you can surely figure it out. So if that's a linear combination of ur plus 1, now there is a different number of them. Now it goes to m instead of n. So this means it's a linear combination of these column vectors, right? Then by exactly the same argument, I can show that xt a will be 0. Because why? Because if I do xt u, I will get zeros here, right? And potentially non-zeros here. But then multiply by sigma, I get zeros everywhere. And of course, multiply by vt, the zeros stay there. So that means that xt is 0, which means that x is from the left null space. So indeed, those are the null spaces, orthonormal bases for the null spaces. And now the null spaces are sort of not really doing anything useful in terms of generating this matrix. So I can as well get rid of them. I can make the decomposition thinner. I can say that this part of the matrix is called UR. I can say that this will be sigma R, and this will be VR. So maybe I will do it graphically. Let me do it sort of more intuitive when it's drawn. So what let's discard the null spaces. The cool thing is it will still work. So here I will have a smaller matrix, another small matrix, and another small matrix. So I took this and I killed the null spaces here, and I killed the zeros there. So this is still an m by n matrix. It's still A. Now this is not an m by m, but it's m by what? R, of course. This is R by R, and this is R by n. So this is UR, this is sigma R, and this is VR transposed. What's the cool thing about sigma R? That's actually why I'm doing this in the first place. The sigma R in this case is invertible, right? In this sigma, no way you could invert it, like a whole bunch of zeros there, right? But this sigma R just goes from sigma 1 to sigma R. That's what the capital sigma R is. And we said that the sigma lowercase r is non-zero. So this entire thing, I can write an inverse, right? I couldn't write an inverse of this. That wouldn't make sense, but I can write an inverse of that. And importantly, by taking this away, I didn't really destroy the property that UR sigma R VR transpose is still A, right? Because these guys were not really contributing anything there. Those were the fluff that was a padding with zeros, essentially, because these guys always hit the zeros in sigma, so they were not generating anything in terms of the matrix A. So this decomposition is still valid. This is sometimes called a compact SVD, because it's like SVD but stripped of the null spaces. And this is sometimes called a full SVD. Okay, and why I'm doing this is because I want to show that these vectors, the column vectors of UR and the column vectors of VR, actually are the basis of the column space and the row space, respectively. So let me explain that. So this compact SVD looks like this. This is UR, sigma R, VR transpose, where this is an M by R matrix, this is an R by R matrix, and this is R by N matrix, and this is of course the input M by N matrix. Now I have to be just a little bit careful. The VR matrix looks like this. So I cannot say it's orthonormal, right? This is my VR. Before I was looking at VR transpose, but the original VR non-transpose looks like this. I cannot say that VR is orthonormal, but I can say that VR has orthonormal columns. In other words, VR transpose VR is identity, right? But not VR transpose, that is not identity. Careful about that, right? If it's not a square matrix, you cannot, this is not true. But VR still is identity. So what I can do with that is I can do AVR equals UR sigma R, right? Here I use the fact that VR is identity. And now I know that sigma R is invertible. So now I can write AVR sigma R inverse is UR, right? Is that what I wanted? Right. So what does that mean? That means that the columns of UR are what? If I take like a first column of UR, the UR is a matrix like this, right? There's some column vectors. This is the first one, this is the second one, and so on. There is some matrix here. Let's just say it's a some matrix here, and A. So what is the first column here is just a linear combination of the columns of A, right? That's how matrix multiplication works. I take the first column from here and I multiply it with the columns of A. If you have a good mental picture of matrix multiplication, you see that immediately. So that means that the columns of U, we write it like this, columns of UR are in the column space of A. So what I'm doing here, I'm justifying the thing I said before, is that I said that these guys are an orthonormal basis for the column space, where they are an orthonormal basis, and I just shown that the UR part, they are in the column space of A, well, then they have to be the orthonormal basis for the column space. Now, in the same spirit, I can also look at UR. The UR is like a shorter in this case, like this, and I also know that UR has orthonormal columns. So UR transpose UR is identity, right? So I can do this. I can say UR transpose A is sigma R VRT. Then I can use the inversion of sigma. So inverse UR transpose A is VRT. And now what does it mean for the rows of VRT? Now the similar argument applies, right? Now does somebody want to say it? What is true about the rows of VRT, aka columns of VR? They are linear combinations of the rows of A, right? Here is some matrix acting on A, and what all the matrix does, it scrambles the rows. It takes linear combinations of the rows, right? So VR are in the row space of A. Here it's just like a little bit confusing because you have the extra transposition here, so you always have to like can look at it either way. So this is showing the last piece of the puzzle here. That's demonstrating that these first R rows from VT are indeed in the row space of A, and therefore they form an orthonormal basis for it. So that's the full picture. That's what ties together SVD and the 4 fundamental subspaces idea. The 4 fundamental subspaces are immediately present in the full SVD, and therefore the SVD completely describes the action of an arbitrary matrix. That's why it's such a powerful thing. Okay, we still have a little bit of time, so I can do an example. It's a very simple example, my favorite 2x2 case. Let's take a simple matrix as this, where we can actually write it on the paper and find its SVD. So what I need to do is to take a look at ATA, right? And ATA, this is easily computed, is this. So note that it's a symmetric matrix, as it has to be. And the eigenvectors are like this. Well, I have only a couple minutes, so I'll just do it a little bit quickly. This corresponds to eigenvalue 8, and there is another eigenvector like this, which corresponds to eigenvalue 2. So notice that they are orthogonal. And what I need to look at is AV1. AV1, if you do the math, it's 2 times square root of 2. After normalization, this is, I can say, the U1 is a normalized version of this. So this is nothing but 1, 0. And AV2 is, after you compute that, you get that 0 square root of 2. So normalizing, I get 0, 1. And from this, I can immediately write the SVD 2, 2, minus 1, 1. So notice it was not a symmetric matrix to begin with, but that SVD could not care less. So I take the U vectors and put them here. So this is just an identity matrix. That's fine. That can be like that. The scale here is 2 times the square root of 2, right? And here the scale is the square root of 2. And here I take the eigenvectors transpose. So if this was V1 and this was V2, then here I have to write V1 transpose, so 1 over square root of 2, and again 1 over square root of 2, and this is V2 transpose, so minus 1 over square root of 2 and 1 over the square root of 2. And obviously, this is obviously orthonormal. You can also see that, you can also check that this is orthonormal. This is diagonal matrix, and this is exactly the SVD decomposition for this matrix. So this special case in this matrix had full rank and was square. So we don't see any null spaces here because the null spaces are trivial in this case. You can also do an example where the matrix has non-trivial null spaces. Actually, you can do this for homework if you want. You can try it on matrix that's like this, 2, 2, 1, 1. Or just plug it in MATLAB and you will get the answer immediately. Okay, we'll do some more examples on SVD applications and some more connections to other things on Monday. SVD is really cool. The other things from linear algebra I pretty much forgot, like these pivots and stuff. Like you learn it and then you barely use it. But SVD is something that you learn, that you use in engineering practice quite a lot. All right, any questions? Okay, so thank you very much. and I will see you on Monday.